So machine learning has quickly taken over a number of fields, things like web search, image recognition, and now it's poised to transform additional areas like healthcare, automobiles, and defense. In particular, sparse machine learning models are very useful for making high-dimensional data easier to analyze. And this results in models that are fairly easy to understand and more generalizable to new data and even new tasks. In many applications, it's important to go further and to interpret a model's predictions. This is important for research and in practice, as we've seen throughout the conference. For example, DARPA has launched the Explainable AI program to make algorithms more transparent. And there's currently an active debate over whether next year's EU General Data Protection Regulation requires a right to an explanation for every machine decision that significantly affects a human. So in this paper, we study sparse explanations as a way to make a given model more interpretable. This can be thought of as a kind of feature selection. Specifically, we define a combinatorial optimization problem which fits in the framework of weak submodular maximization, and design simple streaming algorithms to obtain approximate solutions with provable, data-dependent performance guarantees. First, I'll describe the relevant background for the subset selection problem. Then I'll discuss our results for streaming weak submodular maximization, and finally, I'll show experimental results for interpretable feature selection applied to neural networks. So our goal in this work is to solve the following optimization problem, which is called subset selection. Given a ground set of size n and a function that takes a set as input and returns a non-negative real number, select a set of size k which maximizes f of s. This has many applications like facility location and summarization, but here we focus on sparse regression and neural network interpretability. So one concrete example of this is the problem of interpreting the predictions of a black box neural network. In this example, I retrain the Inception V3 neural network to classify images as one of 5 types of flowers. Now here's an example that contains both sunflowers and daisies, and I'd like to know why the network classifies this image as sunflower instead of daisy. So looking at the final logits, these are the 2 largest values, sunflower and daisy, and sunflower is about 4 times larger than daisy. But why? So now I'll describe how to formulate this as subset selection. Basically, the idea is to partition the image into interpretable chunks using a segmentation algorithm. And then we can define a step function on these segments. So turn on only certain segments of the image and replace the rest with a neutral background, and then we can check the sunflower logic for these new images. So for this random subset of images, of image regions, it's quite low. But then the logic for these 2 image regions, index 25 and 28, is about 1/2, and for these 5 regions, it's about 0.8. And we see the same thing for the label daisy, about 0.6 and 0.87. So more generally, we can define a set function to be the activation for a subset of the image, minus some reference activation. So here, image sub S is an image with the segments, or the image is on the segments indexed by S, and the reference image is on S complement. So if the set is size k, then our explanation uses only k segments. So now, the new goal is to find a subset of image segments which contribute the most to a given label. And we can go from image to segmented image to sparse explanation using a selection algorithm. There are 2 potential issues with this approach. If we make no additional assumptions, then the general subset selection problem is NP-hard and hard to approximate, meaning we need to check all n choose k subsets, exhaustive search, to find the best one. Moreover, in our application, each call to f requires performing inference on a deep neural network, which could take seconds depending on the size of the model, how it's accessed, and how it's stored. So we also want to reduce the number of function evaluations. To address this second issue, we turn to streaming algorithms, which make one pass over the n items in our data. An incoming item is either kept or thrown away forever. They maintain sublinear number of elements in memory, ideally constant, and this minimizes the number of function evaluations. So there's been a lot of related work on guarantees for greedy and streaming approximation algorithms, and I'll discuss some of that here. An algorithm has approximation ratio R if it returns a set with function value that's within a factor R from the optimum value. So here R is between 0 and 1. Clearly, exhaustive search will always have an approximation ratio 1. And previous work has proved that efficient greedy algorithms obtain good approximation ratios when the set function is assumed to be submodular. I'll explain what that means in a minute. So for full random access, the classic greedy algorithm achieves a factor 1 minus 1 over e. And for streaming access, the ratio is 1/2 with an algorithm called CF streaming. For a larger class of functions called gamma weakly submodular set functions, there's a similar approximation guarantee in terms of this parameter gamma, which I'll define soon. So in this paper, we combine the two assumptions and design and analyze streaming algorithms for maximizing gamma weakly submodular functions subject to a cardinality constraint. Specifically, our contributions are as follows. First, an impossibility result, which states that any streaming algorithm with sublinear memory has an arbitrarily low approximation ratio for a worst-case stream order. This differs from the submodular case when we were guaranteed a 1/2 minus epsilon approximation for any stream order. Next, we designed Streak, the first streaming algorithm for maximizing a weakly submodular function with average case constant factor guarantee, assuming a random stream order. This algorithm has approximation ratio in terms of gamma, but does not require the gamma parameter as input. And finally, we conduct experiments to evaluate the algorithm's performance on sparse regression and neural network interpretability. So next, I'll explain the main theoretical background for our work, which is greedy submodular optimization. Many algorithms maximize the following quantity, which is called the discrete derivative of f at b given a. This measures the increase in f when we add b to a. F of a union b minus f of a. And the discrete derivative can be used to quantify diminishing returns. For example, a monotone function is one where f of x given a is non-negative. And for a submodular function, when a is a subset of b, then adding x to a is always larger than or equal to adding x to b. Now, this theory is useful for problems like exemplar-based clustering, but in general, we cannot use submodular functions for applications like sparse regression and the neural network objective I described before. However, under a relaxed version of the previous definition, we can still bound the performance of greedy algorithms. So here's a modified version of the submodularity ratio for two sets S and L, and this was defined in 2011 by Das and Kempe, and this is the key parameter in our analysis. The numerator is the sum of all discrete derivatives adding each element j in S, so j given L, while the denominator is the discrete derivative adding all of S to L, S given L. And so if we only consider sets of size at most k, then we denote this ratio as gamma sub k. With this definition, if the submodularity ratio gamma equals 1 for all sets, so gamma sub n equals 1, then the function is submodular. But as long as gamma is bounded away from 0 for all sets of size less than k, then the function is gamma sub k weakly submodular. And a growing body of work uses this framework to analyze algorithms in various non-submodular applications. So the most relevant related works are Nemhauser's classic greedy algorithm and CF streaming by Badanidiyuru. Approximate submodularity has been very active in the past few years, and interpreting neural networks has also gained attention. There are many different frameworks, including the talk right after this one, and in our experiments we compare to LIME, which is another black box method that solves a related but more expensive optimization problem. So next, I'll describe our results for streaming weak submodular optimization. First, a negative result. In the worst case stream order, we can drive the approximation ratio of any streaming algorithm to 0, so it performs arbitrarily bad. And the precise theorem statement is here. For more details and a proof sketch, please stop by our poster. The surprising thing, compared to previous work, is that for submodular functions, the worst case still has a constant guarantee of 1/2 minus epsilon. But for gamma weakly submodular functions, here the approximation ratio goes to 0. So this motivates us to look at average case performance. And now I'll present our algorithm for streaming weak submodular maximization. And I'll start by first describing a simpler algorithm that we design as a subroutine. So the key idea is to use this discrete derivative I defined before. Each time a new element u arrives, we compute the discrete derivative of adding u to what we have already stored, sg, and then add u to sg if it exceeds a threshold defined by this input parameter, tau. Okay? So we repeat this until we store k items or the stream finishes. And note that the algorithm does not require knowledge of gamma, it only requires tau. So our first positive result is that the expected value of the output set is tau times this constant, which is independent of k and n. Right? This is a good approximation if tau is close to this function of gamma times the optimum value f opt. And our final algorithm removes this dependence by running several instances of threshold greedy at exponentially spaced thresholds. So in particular, at most 1 over epsilon log k instances. So here, m is a running maximum singleton value, and epsilon is an accuracy parameter between 0 and 1, which controls the spacing. I don't have time for the proofs here, but please stop by the poster for more details. So to recap, we have two algorithms with different approximation guarantees, memory requirements, and running time complexity. Threshold greedy can be used when gamma and fopt are known, and streak runs without having to know these values. And then the time and memory increase by a factor 1 over epsilon log k. So finally, I'll show some experiments. Due to time, I'll skip the sparse regression experiments and go to interpretability. So here's the setup from before. We want to go from image to segmented image to a sparse explanation for why a network predicts a given output label. And we run the streak algorithm with the objective function from before and a random stream order of segments. We also compare to Lime, which is a related approach that solves a more expensive optimization problem. It creates many more images and calls many more inference calls to the model, and then fits a sparse linear regression. So here are some example outputs. Here's the model from before running Inception V3 plus transfer learning on another image of a sunflower. And if we compare streak to 3 variations of Lime, we see that the explanations are pretty similar. They all return about 2 sunflowers, but some of the outputs of Lime have this fence and these extra flowers sometimes. And now for the sunflower daisy image from before, predicting the daisy label. So all the algorithms return mostly daisies and a few sunflowers. So we observe that the model is correctly identifying daisies. And now let's compare the running times. So because the Lime optimization problem has to generate thousands of images, we're about 5 to 10 times faster, and we produce similar outputs. So to recap, we prove approximation guarantees for streaming algorithms under the theoretical assumption of weak submodularity, and show experimental results for interpretable image classification and sparse regression. The code is on GitHub. And finally, there are many exciting ideas for future work. First, there's some looseness in the proof technique, and we have ideas for improving the guarantee for these algorithms. Also, we consider other classes of streaming algorithms which use knowledge of gamma as input, allow multiple passes over the data, or use adaptive thresholding. And finally, it would be good to know what is the best approach to interpretability. When do different methods agree, and when do they disagree? And can these combinatorial approaches to interpretability help with problems like fairness and adversarial examples? So for more information, please stop by our poster, number 155 tonight, and thank you for your attention.
Great. Left time for questions. There's mics. So I was wondering how you set the activation threshold.
What do you mean, the activation threshold in the algorithm, or?
Oh, that was the tau? That
yes,
okay.
yeah.
All right.
So yeah, we run several instances with different versions of tau, yes.
Anyone else?
No, we didn't work that out. I guess we have a guarantee assuming gamma, but in general it's hard to compute given an arbitrary data set. Right. Yeah.
All right, great job. I'll ask the next speaker to come up. Let's thank Ethan again.